How do we measure things we can't see, like the nucleus of an atom? So that was your task, to measure the size of the nucleus of an atom without directly measuring it. This is what Rutherford did using some advanced computations, but we're going to use a more straightforward method. So this bend represents the volume of a gold atom, and this fishing sinker represents the nucleus of the gold atom. And we're going to try to measure it indirectly, namely using calculations. So first let's make several throws. I've got 100 or more beads in here that represent the alpha particles being shot at through the gold foil. One, two, three. That's our first hit. So we're going to tally that. One hit. I've thrown it 54 times. And I've hit it once. Let's keep going. $81, $82, $83, $84, $85, $86, comes after $85, $87, $88, $89, $90, $105, $106, $107, $108. I'm going to finish all these alpha particles. 111. 1. Let's see. I think I was at 179. 180. 181. It's harder to do with one hand now. 182. 183. 184. 185. 186. 187. 188. 190. 191. 192. 193. 194. 195. And I'm out of beads. 196. So, stepping on beads. 1 out of 196 alpha particles. Now, if I had a partner, I could have done more in that amount of time, which you all had partners. Let's do the calculations. So the logic is that the probability, which is the number of hits over the number of throws, is directly related to the size of the nucleus over the size of the atom. So in our task, the nucleus was that fishing sinker thing suspended by a thread. And the atom was the bin. So the number of hits was 1 out of 196 throws. Now, certainly if you get this kind of number, we should keep throwing this until we get a few more hits. But I don't want to do that. The point of this is to show you the calculations so you can do those correctly. Now this is what we're solving for, the size of the nucleus. The size of the atom, we'll have to go measure that. So the width of this box is, what would you say? So what I can see is 25.35. That's my estimated digit, is the last digit. I forget what I said. $25.35. Centimeters. That's my length, or my width. So let me get my other length. $33.30. 33.30. So that'll give us the area of the box. We don't need to get the volume because it's not a sphere, it's a rectangular bin, and the depth didn't really matter. If we solve for x, we're going to get this number here. And we'll get the area that way. So when I do that times that divided by that, I get 4.3069, and it keeps going. But we're going to have to trim that using sig figs. So in our measurements, these are the only two things I measured, that number and that number. Right, these have unlimited sig figs because we're just counting. But these were we measured with a ruler in centimeters. So that has 4 significant figures, and that also has 4. And since we're multiplying and dividing, our calculated answer should have 4. So we'll keep the 4, the 3, the 0, and this last one we'll round up to a 7. So there's the area, if that's what we were going for. Now if we want to go for volume, we could just say, if that's the area, then that's also pi r squared. And we can find what radius is. And I would use my stored number, not my rounded number. Take the square root of that, and we get the radius. 1.171 centimeters. Okay, notice we got a square root. Forgot my unit here. Square root of square, and you get that one dimension back. So here's the radius. If our atom was a circle, and if you want to get volume, you can plug. Okay, so let's keep tabs here. There's the area, if you're looking for area, and if you're looking for radius of your nucleus, according to my numbers, 1.171 centimeter, right? And therefore the diameter would be double that, if that's what we're looking for. So that'd be 2.342 centimeters. And then if we were looking for the volume, we could just take that radius. So let's do volume down here. It's 4/3 pi r cubed. And let's plug that in. And if you plug that into your calculator, with the radius being that stored number we calculated earlier, then this is the volume of the nucleus, assuming that it's a sphere, which it is. Let's see how close we were and then calculate the percent error. Looks like the nucleus was 1.80 centimeters. Now I can calculate how close I was, or how off I was, by calculating the percent error. Since I already have the diameter on the screen, I'm going to calculate my percent error using my diameter measurement, which was 2.342 centimeters. So the percent error is my experimental measurement, which is 2.342 centimeters, minus the accepted value. We're going to take the absolute value of that, divided by the accepted value, times 100 to turn that into a percent. And since I only have 3 significant figures in the accepted value, and I'm multiplying and dividing, then my answer also needs to have 3 sig figs. And my percent error was 30.1%. Well, guess I'm not winning any Nobel Prizes anytime soon. See you next time.